friends, we have been talking about the Y-bus matrix formulation for an unbalanced three-phase system. So let's continue. So what we did is we have taken this simple system and we have written all these equations for all these injected currents I1, I2, I3 and I4 at all these 4 buses, and these equations are given by equation 1, equation 2, equation 3 and equation 4. So now let us write down these equations in matrix form. So in matrix form, in matrix form, so I can write down I1 ABC, I2 ABC, I3 ABC, I4 ABC is equal to something. We will write something here, and we will also write something here. What we will do is here V1 ABC, V2 ABC, V3 ABC, V4 ABC. So now before I write it, let us make this grid, so it will be helpful for us. So make this grid, we are just making these grids, just making these grids. Right, so we are just making these grids. So now let's see how it would look like. So if I look at the expression of, let's start. So it is minus y14 V1 ABC, sorry, so it is minus y14 V1 ABC, so it is minus 114 V1 ABC, then minus y34 V3 ABC, minus y34 V3 ABC, and then it was y14 shunt, y14 ABC, so it is y14 shunt ABC plus y14 ABC plus y34 shunt ABC plus y34 ABC, and this is would be a 0, and I3 ABC would be I3 minus y23 V2 ABC, so it is minus y23 V2 ABC, y23 V2 ABC, and it is minus y34 V4 ABC, minus y34 ABC, and this is y14 shunt ABC plus y14 ABC plus y34 ABC plus y34 shunt ABC, and this is again 0. In fact, to make it little neater, we can possibly write, let's say y44 ABC, it is y33 ABC, where y44 ABC is essentially this y14 shunt ABC plus y14 ABC, y14 y34 shunt ABC plus y14 ABC plus y34 shunt ABC plus y34 ABC. Similarly, y33 ABC will be y23 shunt ABC plus y23 ABC, y23 shunt ABC plus y23 ABC plus y34 shunt ABC plus y34 ABC, y34 shunt ABC plus y34 ABC. So now let us write down the equation for I2. I2 ABC is minus y12 V1 ABC minus y12 ABC, then minus y23 V3 ABC minus y23 ABC, it is 0, and this is, let's say, y22 ABC and y22 ABC is given by this one. So y12 shunt ABC plus y12 ABC. So y12 shunt ABC plus y12 ABC plus y23 shunt ABC plus y23 ABC, y23 shunt y23 ABC. Similarly, it would be y11 ABC, and then here for 1, bus number 1, minus y12 minus y14, so minus y12 ABC, it is 0, minus y14 ABC, and y11 ABC is equal to, so it is y12 shunt ABC plus y12 ABC plus y14 shunt ABC plus y14 ABC. So this is the case. So this is the entire matrix form. So now let us look at the certain other details. Each of them is 3 cross 1. Each of them is 3 cross 1. Each of them. So then therefore its total is 12 cross 1. Similarly, each of them here is 3 cross 1. So then therefore this is 12 cross 1. Similarly, here all these matrices, everything is 3 cross 3. Everything is 3 cross 3. All of them are 3 cross 3. Similarly, please note that this 0 is actually 3 cross 3 null matrix. All these zeros are 3 cross 3 null matrix. All are 3 cross 3 null matrix. Similarly, this is 3 cross 3. Similarly, this is 3 cross 3. So then therefore this is 12 cross 12. Now here we had n is equal to 4. So then therefore here in this case, so now so then therefore this one is nothing but the bus injection vector. We call it I ABC vector. We call it I ABC vector. This is the bus voltage vector. We call it VABC vector. This is a vector, and this is nothing but the Y ABC, right? So then therefore IABC is 12 cross 1, which is nothing but 3 into 4. Y bus is 12 cross 12, which is nothing but 3 into 4 cross 3 into 4, and VABC is 12 cross 1, which is equal to 3 into 4 cross 1. So then therefore, for an n bus system, so for n bus system, I bus vector, IABC vector is 3n cross 1, VABC vector is 3n cross 1, and YABC matrix is 3n cross 3n. So we should say that this is 3-phase injection current vector. So this is 3-phase injection current vector. This is 3-phase bus voltage vector, and this is 3-phase bus impedance matrix. So this is the first observation, where n is the number of bus. So this is the first observation. Now what about the entries? Entries are actually, you see that whenever there is a direct connection between any two bus, at the off diagonal term, essentially the negative of the admittance matrix is there. For example, here there is a direct connection between bus 1 and 2, and as well as there is another direct connection between bus 1 and 4. So then therefore, in this, if I say that this is 1 2 position, so then here it is basically negative of this series admittance matrix is there. Similarly, here also negative of this series admittance matrix is here, and these diagonal elements, this and this, these 4 are called the diagonal elements. I mean, but again these diagonal elements are actually essentially these are diagonal 3 cross 3 matrix. These are all actually diagonal, but 3 cross 3 matrix. This is also 3 cross 3 matrix. So when this diagonal 3 cross 3 matrix is nothing but the sum total of all the diagonal this diagonal 3 cross 3 matrix are nothing but the sum total of all the 3 cross 3 admittance matrices directly connected to that bus. So then therefore, as we can see, the rule for building up the 3-phase admittance matrix exactly follows the rule for building up the single phase admittance matrix. In the case of single phase admittance matrix also, the diagonal term is nothing but the sum total of the admittances connected at any particular bus, and the off diagonal terms are nothing but the negative of the admittance connected between any two buses. Here in this case also, the diagonal 3 cross 3 matrix is nothing but the sum total of all 3 cross 3 admittance matrices connected directly to that particular bus, and the off diagonal 3 cross 3 matrix is nothing but the negative of the 3 cross 3 admittance matrix, 3 cross 3 series admittance matrix connected between any two buses. So by this small example, we know that it is very easy to find out the bus admittance matrix of any 3-phase system in which there are only lines. In fact, I mean, this particular method can be very easily programmed in a computer. But now the question is, here so far in this diagram, we have not considered the presence of any transformer. But in any system there is a transformer. So then therefore, we need to also take into account the presence of the transformer in this particular Y bus formulation. So, let us look at that how to consider transformers. So, the next the next is that consideration of transformer in Y bus matrix. So, the next step is consideration of transformer, consideration of 3-phase transformers in Y bus. So, now let us say that we have a bus, we have two buses, let us say bus M and N, and between, please note that this is basically a 3-phase bus. So, then its voltage is again Vm ABC, this voltage is again Vn ABC, and between these two buses there is one 3-phase transformer is connected, and this 3-phase transformer can have any connection. It can have star delta, star star, star grounded, star 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 grounded, delta star grounded, delta star ungrounded, anything and everything it can have. Now, as usual we have got, so now we have got Vm ABC and Vn ABC. When we are modeling the transformer, what we do is we denote some current here which is going into the transformer from these two buses. So, let us say that we denote this because this is a 3-phase transformer. So, then where although we are showing in one single phase line, but then it is actually a 3-phase line. So, then therefore, there will be a current I1 ABC and there also would be a current I2 ABC. Of course, I1 ABC is I1A, I1B, I1C transpose, and I2 ABC also I2A, I2B, I2C transpose. So, these are all 3×1. So, now what we have is, so now I have got actually 6 voltage quantities. What are these 6 voltage quantity? It is VMA, VMB, VMC, VNA, VNB, VNC, and 6 current quantities I1A, I1B, I1C, I2A, I2B, I2C. So, then therefore, if I do write down the equation I1A, I1B, I1C, I2A, I2B, I2C. So, these are the 6 current quantities. Please note that all these currents are complex current. So, because this is a 6×1, and here also we have got V1A, V1B, sorry, this should be VM, VM. So, this should be VMA, VMB, VMC, VNA, VNB, VNC. So, this is also a 6×1. So, now obviously this matrix would be 6×6 matrix. So, now what happens that depending upon the transformer connection, right, there will be altogether 36 elements. Now, these elements may be 0, these elements may be non-zero, right. What these elements would be, that would depend on actually the particular transformer connection, but there will be altogether 36 elements. Again I repeat, these elements may be 0, these elements may be non-zero, but there will be altogether 36 elements, and these 36 elements are denoted like this. Now, what we do is that we do partition these 36 elements like this, and we call that it is y1. Please note that this is a 3 cross 3 matrix. We call that it is y2, we say call it is y3, and we call it is y4. Please note that these matrices y1, y2, y3, y4, they would be known, they are known for a particular type of connection. We will try to see in this lecture if we can give 1 or 2 examples, that what would be the matrices for any let us say one particular type of transformer connection. But right now, for the purpose of our analysis, let us assume that for a given particular transformer connection, these matrices these matrices y1, y2, y3, y4 are all known, and we all know that this is all 3 cross 3 matrix. These are all 3 cross 3 matrix, 3 cross 3, 3 cross 3. So then therefore, now of course, now this is, as we said, that this is I1 ABC, this is I2 ABC, this is VM ABC, and this is Vn ABC. So then therefore, this entire relationship can be written very succinctly as I1 ABC, I2 ABC is equal to Y1, Y2, Y3, Y4, and this is VM ABC and Vn ABC. So this is the transformer model. So then therefore, we can write down that I1 ABC is equal to Y1 Vm ABC plus I2 Vn ABC. Similarly, I2 ABC is equal to Y3 into Vm ABC plus Y4 into Vn ABC. So these are the guiding equations, or these are the modeling equations for a transformer. So now let us take a small example. Let's take a small example again, but some other example. Let's say now everything we are considering as a 3-phase system. So now let's say bus 1, let's say bus 2, let's say bus 3, and let's say bus 4, and let's say there is an bus 5. And so this is bus 1. Please note that these are all 3-phase system, so we are not writing them specifically. Bus 4, bus 5, in between there is a line, 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 but in between there is a transformer. So now you would like to find out what is their bus impedance matrix. So again, as usual, we take that this is current is I1 ABC, this current is I2 ABC, so this current is I2 ABC, okay, and this current is I3 ABC, this is I4 ABC, this is I5 ABC, and these voltages are V1 ABC, V1 ABC, V2 ABC, V3 ABC, etc., etc. And all these lines, I mean there are 4 lines, 1, 2, 3, 4, all these lines are represented by their equivalent pi model. So then therefore line models are, as we have just now seen, that essentially Y MN ABC and Y MN shunt ABC. So M and N would be, can be, so then here M and N values would be for the first line 1 2, the second line 3 4, then the third line let's say 1 5, and the fourth line is 4 5. So these are the 4 lines, and these are the different values of Y M N ABC. So then with this we are now ready to find out that what would be the bus impedance, or rather the bus admittance matrix. So now as we have done earlier, so we can write down that I1 ABC is, so we can write down that I1 ABC is actually, as we know now, it is now very simple, that it is nothing but Y11 ABC into V1 ABC minus Y12 ABC into V2 ABC minus Y15 ABC minus Y15 ABC into V5 ABC, and Y11 ABC would be nothing but Y12 ABC plus Y12 shunt ABC plus Y15 ABC, plus Y15 shunt ABC. So this is the bus 1. So this is bus 1. So then similarly we will have to write down the equations corresponding to bus 2, bus 3, bus 4, bus 5, and we will be now writing utilizing these conventions. So it will be now written quickly. So then after that we write all the equations corresponding to bus 2, bus 3, bus 4 and bus 5, then we will club them together in Y bus matrix and then see that what particular conclusion we can take. So we will do this in the next lecture. So thank you so much.